UC Riverside, talking about the lightweight cardinality estimation in LSM-based systems.
Thank you. Hey, my name is IIdar, and today I'm going to be presenting our work, joint work with colleagues from Riverside and Irvine, and I'm going to be talking about statistics and databases. So if we look at this problem and go back to early system R days, and kind of see that not that much changed in those 40 years. So the usual way of getting stats is just do this run stats approach. And also, but over those 40 years, the differences in storage architectures in database systems, it evolved. So initially, this approach assumed that we have the update in place storage, which we know can cause some random IOs. And right now, more systems adopt log structured storage in order to handle the high write throughput because the data sets, for their workloads, they have the better performance. But the traditional approach to do stats basically relied on this in-place update storage. So that's the question, how would we design the statistics collection framework for those LSM systems? So what is this traditional approach? So this is just, I call it run analyze type of thing. So it basically performs, it scans your data, does the sorting in order to produce some kind of statistical synopsis. So what's wrong with that approach is that because it does this data scan, it requires the inherent additional I/O. And yes, we can do sample and alleviate that problem to some extent, but still there will be some overhead associated with that. Additionally, this approach is inherently manual. So you have to hire some DBA to run that for you, or maybe you can put it on an automatic schedule, do it at 2 a.m. in the morning, but maybe you have some queries running that, and that can interfere, data scan can interfere with your valid workload, query workload. And lastly, for the workloads which are experiencing a lot of updates, the statistics that you're getting, they're essentially a snapshot of the data that you have right now. And they will eventually go stale. So you have to, so you have to recompute it every so often. Maybe you can introduce kind of a notion of a batch and recompute it after the batch, but the question is how to pick the size of that batch, if your workload is varied, and maybe it's not even regular. So let's go back to the kind of storage life cycle for the LSM systems. So I probably don't have to go into that much details, but basically it boils down to a couple of things. So first, the inserts, deletes, and updates, they're batched in memory components. And if the records are present in those memory components, the modifications are done entirely in memory, in place, but otherwise, if they're already on the disk, we just append a special tombstone or antimatter record, or append a new version of the record. And once the memory component gets full, we flush it contents on the disk, and also we have the periodical merge compaction process as well. Right. So this is a small example of the LSM workload. So on the left we have new entries coming in. They populate the contents of in-memory component. Let's say, for example, we have 2. Here is the maximum number of records that memory component can hold. So after that, the flush process will be triggered. That will read the contents of that memory component and do some modification in order to create a disk representation for that and put it on the disk as first disk component. As we're getting, we also can get deletes or updates for the previous entries. And for deletes, as I told you, we get this antimatter record and the new version for updated record. And that as well going to be eventually flushed to the disk. And finally, we have this merge process where we read the contents of the previous components and reconcile the older version of the older versions to produce the merged representation of the new component. So you can kind of see that in this life cycle, there's kind of inherent data flow going on from memory to the disk, and data is always immutable. So our solution to the problem of statistics is that actually we want to tap into that data flow and gather those statistics during those LSM lifecycle events such as flush and merge. And what are the advantages of that is we kind of hide our computation, the computation of synopsis behind this compulsory processing that's already done in the system. And again, this is already existing data flow, so system, like engineering cost of that is pretty low because there's already a bunch of moving parts in the system which does many things for us. And it also naturally keeps our statistics up to date because now they're tied to the actual data flow in the system. So some of the design considerations that we had when we proposed this solution is that first and foremost, we want to keep those statistics collection lightweight. And how we're going to do that is first we're not going to do any collection, SAS collection on the in-memory modifications because it's a critical path, critical insert path, so we don't want to mess with that. And also the contents of the size of those in-memory components are pretty small comparative to the overall data set size. So we're going to lose on the accuracy, but it's we can tolerate that. And secondly, in order to avoid this kind of sorting and producing the synopsis, we want to leverage the sorted order that provided by the indexes in those LSM components. And so that's our collection methods can benefit from that sorted order. Also, we wanted to build a framework which is generic enough so you can plug in your synopsis collection algorithm and run different algorithms, compare them. Obviously, we want to do the want to operate in the distributed environment, shared nothing environment, and because we're now tied to the LSM, we have to correctly manage the antimatter records. So this is a quick picture showing how they're getting those tasks. So basically, when we're going to be flushing this component, in addition to creating a new disk component, we'll just create a piece of statistics, which will describe the distribution of data that resides in that particular component. And if we have a component which has antimatter records, there we kind of split the data flow into two parts, the one which describes the regular entries, the one which describes the antimatter entries. And each of those produce their own piece of statistics. And during the merge, what we do is we create the new statistics on the merged component and discard the old one. And the reason for that is because already the system does this merge and reconciliation anyway. So again, we have this stream of records which are already reconciled. So we can, again, tap into that stream and produce a new piece of statistics. And that also helps us to get more accuracy. And finally, the kind of read path for that is how we're going to use those statistics is, so the collection happens on the, so this is a shared nothing architecture, so the collection happens on the individual nodes. And once those statistics are collected, they're sent over the network to the master node, which stores them into the catalog. And once the query comes in, we can produce the estimate for cardinality of this query just by getting estimates from the individual pieces of statistics. And you can see that for statistics describing the antimatter records, we subtract that from the total estimate. So some of the implementation details about the approach. So we implemented a couple of different algorithms to capture those stats. So first is streaming histograms, both equi-read and equi-hide. Also developed our own prefix wavelet decomposition, some wavelet decomposition algorithm. We did this prototype in Apache Asterisk DB, and the prototype collects stats on non-composite keys of primary and secondary B-tree keys, which are also restricted to integer numerics. So during our experiments, we basically had like three main stages. So first, to prepare some DDLs, create those indexes for which we use which are helping to collect our stats. Then we do ingest the data and then query it and see what's the accuracy. So thus, there are two main experiments that we do. Is first, how the statistics collection influences on the ingestion. Is there any overhead on that? And second is, what's the accuracy of the estimation? So this shows the overhead experiments. So we had two different types of workloads for our ingestion. So the first is bulk coding, creating the index from the scratch, kind of creating the binary tree in a bottom-up fashion. And we also have a kind of a continuous channel which inserts entry one at a time, top to bottom. And we had two versions of those with kind of two different sources. One is the network socket, and the other is file on the disk. And you kind of can see that none of the statistic collections algorithms introduce any overhead in both cases, both for bulk coding and for feed injection. Going next to the accuracy experiments, we tried different kind of generated data with varied, and in the generated records we varied the distribution for frequencies of the records and both values of those records. And we also tried the real data set from WorldCup 98 server logs. In order to measure the accuracy, we issue 1,000 range queries and calculate the average absolute error on those queries. There are a few different types that we consider. Fixed length queries, kind of the queries with fixed beginning or fixed end, but open end and open beginning respectively. Random queries and kind of degenerative with point queries. I will not going to be touching this, but the full details in the paper. So this is one of the graphs showing the accuracy for the data set with zip skewed frequency distribution, and we varied different value distributions here, and also increased the size of the synopsis in terms of buckets for the histogram or coefficients for the wavelets. And you can see, like in a uniform case, pretty much everyone does okay, but in skewed cases, pretty much everything on the right, we can see that if we increase the size of the synopsis, obviously we can get better accuracy, and wavelets tend to do better in those skewed cases if they have enough coefficients. And so finally, this is the real-world data set. There we don't have different distributions. We have different fields in this data set, and here, because it's a real-world data set, it's a little bit messier in terms of accuracy. For equivalent histogram, pretty much nothing changes because everything falls into one bucket, which is kind of bad. And depending on a particular field, increasing the size of synopsis can make the overall estimation error less, but for some kind of heavily skewed cases, it's not getting better. So, kind of final takeaways that we demonstrated that in systems based on the LSM storage, there is a way basically to get those statistics for free by piggybacking on the events of the LSM framework. We have prototyped this lightweight approach by collecting stats on index attributes, and we created a generic synopsis oblivious framework to collect those stats. And with that, I'd be happy to answer the question.
Quick question. Have you considered any stats that are hard to maintain incrementally?
So in this framework, as I told during the merge, we don't do incremental stats. We just recompute it from the scratch. So there's no point of incrementally maintaining them, because from basically you can think of it as a like function which has the input and output is the synopsis. There's no,
The reason I ask is because I saw the way you calculated stats are based on the old value, and you do some minus the old value and add the new value. So I'm wondering, is it a general approach for all the stats that you are considering here?
Not in this case. So yes, so you're right. So if there we have the kind of deleted entries, we subtract those things. But as kind of the work, as the workflow, your workflow evolves in time, so you periodically get those merges, which in some cases reconciles those deleted entries. And as you get this merge, that's where you again piggyback on the kind of merged result, and this is your new. So you describe the statistical distribution of things in that kind of merged stream, quote unquote. So that's, you don't have to do it incrementally in this case. Again, because merge provides you with the reconciled stream.
The assumption here is that you can merge the states easily, if the states cannot be easily merged.
Right, yes. So for some of the synopsis, or like wavelets can be merged, the equivalent histogram can be merged as well. So the merging part will kind of hit you on the querying side, because that's where, if you have like 1,000 different components, you have to do 1,000 different queries for each of those. So that's where it's going to hit you. But in our experiments, we've seen that probably you don't want to keep the number, because the statistics are tied to the components, probably don't want to keep awful lot of those components, because that's going to be hitting you on the query side, on the query latency, basically. So as long as number of those components is small enough, the overhead during the kernel estimation would be small enough as well.